Adam Rees on the universe and our understanding of it. Excluding the measurement errors, there remains the real and exciting possibility that we have misunderstood the universe. A Nobel Prize winner warns us. The James Webb Telescope shows us evidence that something strange is going on in the universe. If we believe the latest measurements from the James Webb Telescope, then our cosmos would have shifted in such a strange way that there is simply no explanation for it. But what would that mean in concrete terms? Are we really powerless against the latest developments, or do we perhaps already have a new explanation? Adam Rees is one of the leading cosmologists of our time. Years ago, the Nobel Prize winner presented groundbreaking work on the expansion of the universe and discovered alarming discrepancies in the measurements of the Hubble constant. These differences from earlier measurements became known as the Hubble tension. Rees, along with thousands of other scientists around the world, eagerly awaited the launch of the James Webb Telescope. The new technology would finally provide proof of the true nature of the universe. Answers to questions such as, were Rees's measurements wrong, or were the older measurements wrong, should finally bring us clarity. Of course, it was also conceivable that the Hubble tension was a previously unexplained phenomenon, but nobody wanted to face that fact at the time. The Webb telescope shocked scientists because the latest measurements confirmed the accuracy of all previous measurements, and thus a pure measurement error could be ruled out more and more. The differences in the measurements certainly do not occur because our telescopes measure incorrectly. Hubble and Webb each made two measurements, once using Cepheids as standard candles and once using Type 1a supernovae. In this context, standard candles are measurement constants that scientists use to achieve exact measurement results in the universe using the absolute brightness of these phenomena. Actually, both measurement methods should show similar results. What was measured was the expansion of the universe, or rather, the rate at which the universe is expanding and how it's accelerating or decelerating in the process. Minor measurement differences would have indicated a difference in the absolute brightness of the standard candle and would have been physically explainable. But the difference is so great that Adam Rees suspects that the Hubble tension is pointing us to other fundamental misunderstandings about the universe. Adam Rees has found the explanation. Did you know that Adam Rees is the father of dark energy? In 2011, Rees shared the Nobel Prize in Physics with Saul Perlmutter and Brian Schmidt. The three scientists were honored for their special discovery that the universe is not only expanding, but is doing so at an increasing rate. This realization also shocked the researchers, because actually the universe should be slowing down. Imagine how the Big Bang was an initial energy and then the universe races off, forming matter and taking up an ever-increasing space. According to our current physics, it should actually slow down at some point. This idea that the universe will eventually run out of steam, so to speak, led to the Big Freeze theory, in which the universe will end up in a kind of state of shock at some point in the distant future. When all energy is used up, all processes come to a halt and the universe practically freezes. But the measurements taken by Rees and his colleagues showed that the expansion of the universe is not slowing down, it's accelerating. But how can that be? This counterintuitive fact led to the introduction of the concept of dark energy. This force, which no one has yet seen or measured, is thought to be responsible for the mysterious accelerated expansion of the universe. To confirm these theories, the Hubble Space Telescope was used before the launch of the James Webb Telescope. Adam Rees works not only as a professor of astronomy at Johns Hopkins University, but also at the Space Telescope Science Institute, which is responsible for the Hubble Space Telescope. The James Webb Telescope confirms Rees's theory. Think for a moment about your view of the cosmos. Do you also imagine a space in which there are objects that rotate, turn, are created and destroyed? And can you perceive that this space is getting bigger and bigger? This is a notion that may seem a bit crazy to us, but it is a fact. The universe shows evidence on many levels of an expansion of the total space it occupies. Until now, The only logical explanation for these effects was that the universe expands from a starting point, but as already mentioned, the universe would then have to slow down at some point, or at least it should not expand faster and faster forever. This is where the James Webb Space Telescope and its unique mission come into play. In the 2 years of operation, NASA's newest telescope has already shown us many phenomena that confirm Rees's theory. These include galaxies that are so old that they shouldn't really exist. Furthermore, so far, there has been no sign of a dark age or of real relics of the Big Bang. Thanks to Webb, we can see clusters of galaxies that are so vast and so large that they challenge the theory of an isotropic universe. All this, together with the phenomenon of the Hubble tension, confirms the assumption that we simply did not understand the universe correctly so far. These new findings will now possibly lead to fundamental changes in science. It is not only Adam Rees who sees that the scientific understanding of the world and the universe is currently facing major challenges. Throughout science, more and more researchers admit that more and more unsolved puzzles in cosmology are forcing us to rethink. Radical changes in the universe confirm it. Who would have thought that a simple telescope could cause our entire cosmology to collapse? Although the James Webb Space Telescope is not just any instrument, but the best telescope we humans have ever built, nobody expected these observations. It's as if a completely different universe is suddenly appearing before the researchers' eyes than the one they thought they knew. There are indications that the universe is older than assumed, and that galaxies were formed faster and differently than previous theories had predicted. We may even have to get used to the idea that the universe is infinite. Perhaps we don't even come close to understanding how matter really comes into being. James Webb also provides observations that cast doubt on the existence of dark matter. If dark matter does not really exist, another pillar of the old theories will have been lost. But how can we then explain the phenomena that led to the invention of this mysterious matter? It was researchers like Edwin Hubble and Fritz Zwicky who predicted that there must be an invisible form of matter. Only with the help of this form of matter could the incoherent rotational behavior of galaxies and some other phenomena be explained. There are some other approaches to explaining these phenomena without the existence of dark matter, but they are not quite as coherent. Webb also shows us that the assumption that the universe looks the same in all directions could be flawed. This effect of uniformity is what scientists call isotropy. If this isotropy does not exist either, then the old cosmological model is shaken even further. In the early 2000s, Rees and other researchers introduced the concept of dark energy to explain the accelerated expansion of the universe. However, the existence of this form of energy is still unproven, just like the existence of dark matter. Due to these new discoveries, it's expected that the standard model of cosmology will soon be fundamentally revised. But where could this change lead us now? These new worldviews amaze us. Imagine we live in a cosmos in which not a single physical constant is correct. That would mean that Einstein's theory of the constant speed of light is not true, that standard candles can never produce the same results, and that physics changes regionally and even over time within our cosmos. Such considerations arose after the latest measurement results of the JWST, and the latest theories go even further. In addition to the idea that our physics can only describe a part or an epoch of the universe, there are approaches that see intelligent forces in dark matter or dark energy. This would mean that our cosmos has something like a soul or its own intelligence, which in turn could explain who created the universe in the first place and why. We would still be a long way from having real answers to our questions after such insights. But if such crazy assumptions were confirmed, we would at least know that there is such a thing as a creator intelligence. Until now, we have always looked into the light and into matter to understand the universe. But now, it is becoming apparent that the structures we are looking for prevail in the mysterious darkness of the universe, of all places. However, this has not really been proven either, and we will have to continue to observe what is unfolding before our eyes what measurement results we get from the latest Webb observations, and what that means for our science. We humans have begun to explore our surroundings and, at some point, the universe because we wanted answers to the questions of who or what created it and why it exists. We may now be at a turning point that changes our old worldview so dramatically that it resembles a revolution in knowledge and science. Less daring theories simply state that our universe is much older, or that it may have no beginning and no end. But where do the signs of expansion come from? Here too, there are exciting new ideas that suggest that our cosmos is subject to regional currents. You can imagine it something like a wafting bubble formation that contracts or expands regionally, reaching different rates of acceleration and expansion. If there never was a Big Bang, it makes perfect sense. It is hardly surprising that there has been no real evidence for the Big Bang either. Only the fact that, for a while, all the theories fitted together quite well seemed to confirm the idea of a starting point some 13.8 billion years ago. But we have never seen any real evidence for it. If we take another look at quantum and particle physics, we find further evidence that something is wrong with our old worldview. From the quantum world, we know that our universe must be far more changeable and flexible than previously. Adam Rees is probably one of the few researchers who is keeping a cool head these days. Since the launch of the James Webb Space Telescope, nothing is as it used to be. The universe is probably much older than assumed. Galaxies have formed much faster and quite differently than all our predictions. And our cosmos may not be expanding from a single point. What happens now if dark matter is possibly still a mistake, and James Webb is already presenting the next picture of inexplicable phenomena in the cosmos? Adam Rees is one of the leading experts in the field of research into the expanding universe. His contribution to the discovery of the accelerating expansion of the universe revolutionized our view of the expansion of the cosmos and was one of the cornerstones of the Hubble excitement. Rees welcomes the telescope's latest discoveries because he knows from his own decades of dedicated work that our cosmology is flawed. He was involved in surveying the cosmos and using supernovae as standard candles for the first time. In this context, standard candles are something like cosmic scales that scientists use to measure movements and distances in the universe. Using supernovae as a yardstick, astonishingly precise measurement results could be achieved. But one problem remained. Rees and his team found that the expansion of the universe was increasing regionally instead of decreasing. In the course of their work, another phenomenon became apparent, as Rees's measurement results differed significantly from those based on the redshift method. This should not really be the case. Today, we know the differences in the measurement results as the Hubble voltage. Rees's work was so phenomenal that he was awarded a Nobel Prize in Physics in 2011 together with his colleagues Saul Perlmutter and Brian P. Schmidt. In fact, he received the award for the discovery of the accelerated expansion of the universe. Rees and Schmidt are members of the High-Z supernova search team, which is researching techniques to refine the measures of distance in the universe. Perlmutter, on the other hand, came to the same conclusions at around the same time as part of the supernova cosmology project. They observed type Ia supernovae, very bright, exploding stars that serve as reliable indicators of distances in the universe. These observations provided the surprising evidence that the rate of expansion of the universe is increasing rather than decreasing due to the gravitational effects of matter in the universe as previously thought. Bad mistake. The isotropic universe? The biggest crisis in modern science was slowly brewing, and now the bomb has exploded. Instead of answers, astronomers and cosmologists are constantly being served up new puzzles and shocks these days. Now the concept of an isotropic universe is also on the brink of collapse, and with it one of the fundamental pillars of our cosmology. Isotropy assumes that the universe looks the same in all directions, regardless of where you look at it from. This assumption is a fundamental part of the cosmological principle, which states that the universe is homogeneous and isotropic if we look at it on a large enough scale. For example, the cosmic microwave background radiation pattern looks uniform everywhere, and large clusters of galaxies are also distributed almost uniformly across space. At least that's how it used to look, and scientists then turned these observations into basic mathematical rules to simplify scientific descriptions of the universe. But this may have been a stupid mistake. The observations of Adam Rees and other scientists researching accelerated expansion have initially confirmed the isotropic model, at least in part because the measurements of supernovae have shown consistent results with regard to the rate of expansion. This means that there appears to be some kind of isotropy. However, the expansion is much faster than it should be according to old physical assumptions. The end of dark energy? It remains exciting in science. In order to understand the puzzle of the new cosmology, we need to take a closer look at dark energy. The exact nature of this energy is still unknown, but its existence and properties are crucial if we want to understand how and why the universe expands in an isotropic way, and why researchers came up with the current standard model of cosmology. Dark energy is a hypothetical form of energy that could be present anywhere in the universe and very likely plays a key role in current theories about the expansion of the universe. It's thought to be the driving force behind the accelerated expansion of the universe. By acting against gravity, it pushes the cosmos apart. In current cosmological theory, dark energy is responsible for about 68% of the total energy content of the universe. Here you can already see a problem. Scientists blame almost 70% of the energy processes in the universe on an energy whose existence has never been proven. An important element supporting the existence and properties of dark energy up to now was the observation of Type 1a supernovae as carried out by Adam Rees and colleagues. The accelerated expansion observed here could not be explained without the effect of a large repulsive force. Further evidence that this mysterious energy really exists was provided by the cosmic microwave background radiation and other large-scale structural studies. However, recent observations by the James Webb Space Telescope have now shaken the concept of dark energy. The JWST can observe the early universe in a level of detail that was previously unattainable. Even the first precise observations revealed structures and objects that are older and more developed than they should be according to the standard model of cosmology. These observations could indicate that the universe may have expanded even faster or originated at an earlier time than previously assumed. All these results indicate that we have not yet understood some crucial elements and forces in the cosmos, including dark matter and dark energy. It's very likely that we are now facing a complete revision of the standard cosmological model, but we are not ready for that at the moment. We can't come up with new theories because we don't have enough tangible information about what's new. Will we find the answer in the world of quarks? So the revolution in our worldview will have to wait a little longer. Only when Webb provides us with more images and researchers make even more incredible discoveries will we be able to piece together a new picture. That may take time. In the meantime, researchers around the world are searching for answers that are already available. David Gross is another scientist who welcomes the crisis and sees it as an opportunity. Gross points out that the answers to the great mysteries of the universe are not hidden in the macrocosm, but in the microcosm. The renowned theoretical physicist is an expert in the theory of strong interaction and string theory. He is also one of the Nobel Prize winners and received the award in 2004 for the discovery of asymptotic freedom in the theory of strong interaction. The discovery was fundamental to understanding the behavior of quarks, which are the basic building blocks of protons and neutrons. These particles are the main actors in the standard model of particle physics, and they are the basis of everything we can see and measure in space. Consequently, the basic structures and principles of the macrocosm must also have counterparts in the subatomic realms. The concepts that Gross helped to develop deal, among other things, with the events shortly after the Big Bang. Realize that there were no stars and no objects in the universe at that time. For hundreds of thousands of years, there was only an extremely hot primordial soup in which particles flitted freely through space without forming bonds. Before the Big Bang, there was presumably only a kind of quantum fluctuation in which all forms canceled each other out in such a way that, from a physical point of view, they amounted to zero. With the Big Bang, this quantum fluctuation fell apart, and particles packed with charges and forces shot into an otherwise empty space. These particles later became stars, galaxies, planets, and life forms like us humans. Is Gross right when he says that these particles are the answers to all the questions? Probably yes, but how do we study the behavior of particles that were in space 13.8 billion years ago? Among other things, researchers use the cosmic microwave background radiation. This is considered to be a fairly accurate reflection of the events shortly after the Big Bang, and has probably not changed much since then. However, quantum physicists and classical physicists do not quite agree on how to interpret this imprint of the early days of the universe. At the moment, the situation in science is that quantum and particle physics cannot be reconciled with traditional cosmology. The findings from the world of formed matter do not fit with quantum physics, or rather, the binding link is missing. David Gross is convinced that this bridge can be found in previously unknown particles and forces. He was one of the researchers who worked hard to reach a consensus between the disciplines even before the debate triggered by James Webb. As co-author of string theory and in a coherent unification of quantum mechanics and general relativity, he was keen to close the gap between the two worlds and disciplines of science. Gross's work on asymptotic freedom describes how quarks behave at very high energies. This is fundamental to understanding the early universe shortly after the Big Bang, when energies were extremely high. His theories can clarify as yet unclear aspects of the expansion of the universe. However, there is some controversy among scientists, as the theses of string theory are too far-fetched for many classical physicists. David Gross suspects that the answers to all unanswered questions lie in the quantum fluctuations within the microwave background. The CMB fills the entire universe and can be found in all directions around us. The Cosmic Background Explorer satellite, which was active from 1989 to 1993, was the first to notice tiny fluctuations in the temperature of the radiation. From 2001 to 2010, the Wilkinson Microwave Anisotropy Probe researched to find evidence of the Big Bang in these fluctuations, and, most recently, the Planck satellite provided one of the most detailed maps of the CMB. However, there is still disagreement among researchers as to how this data should be interpreted. While some claim to have found the necessary evidence for the Big Bang in the CMB, what happened to Voyager 1? According to NASA, the probe is sending a strange signal from interstellar space. Could this be the first indication of an encounter of the third kind, or are we just dealing with a technical fault? Never before has a probe been in interstellar space. Voyager 1 is the first man-made object to send data from there, and it's confusing. What if the interstellar medium is completely different from what scientists previously thought? Will we then have to rewrite the textbooks and prepare ourselves for further discoveries that challenge our imagination? Imagine how a brave probe has been traveling through space for more than 40 years and has now wandered far beyond the boundaries of our solar system. Then suddenly, the probe begins to send a mysterious and inexplicable sequence of signals to Earth. Voyager 1, the furthest man-made object from Earth, transmitted a strange sequence of ones and zeros to Earth almost half a century after its launch. What had happened? The binary code was designed in a pattern that made no recognizable sense to the scientists. All at once, the NASA scientists and engineers were faced with a puzzle. Had Voyager encountered something strange, or was the probe just broken? The second problem was how to diagnose and fix a problem when the device was 24 billion kilometers away in interstellar space. The situation surrounding Voyager 1 presented NASA with a lot of challenges. When the NASA control team first learned of the unusual signals from the Voyager 1 probe, the feverish search for solutions began. They began to analyze the structure of the mysterious messages, hoping to discover in the pattern a clue to the underlying disturbance. The problem appeared complex, so the NASA team turned to artificial intelligence to help them sift through the data patterns using a specialized algorithm. The AI became a crucial tool in deciphering the signals. After days of intensive data analysis, a recurring pattern was recognized, and this was the first indication of a malfunction in the probe's communication hardware. The team developed a hypothesis that a defect in the telemetry modulation unit, the device responsible for converting and sending data from the probe to Earth, could be the cause of the distorted signals. The next challenge was to find a solution to fix this defect remotely. To understand the technical details, engineers dug out ancient blueprints from the archives. Some of the data had long since disappeared or been destroyed, so even former NASA engineers who had long since retired were called back in to solve Voyager's problem. After several simulations and tests, the team decided on a bold approach. They tried to instruct the probe to switch to a previously unused communication system that had long ago been programmed as a backup for just such emergencies. This operation was dangerous because this measure could have meant the end of communication with Voyager. Then a mission of a century would have ended sooner than anyone had hoped. Holding their breath, the team sent the order to switch over the communication systems, and then the long wait began. Due to the enormous distances involved, a signal now takes over 17 hours to reach the probe and another 17 hours to return. We can all well imagine the tension in NASA's control room and the joy when Voyager 1 responded. It was a moment of collective relief and joy that will go down in NASA history forever. The spacecraft had successfully received and implemented the command, and the data began to flow again in an intelligible format. The mission could continue. Further into space than ever before. It's magical. The solution to the problem will give us years more of data from a space that has not yet been explored. Voyager offers us the unique opportunity to receive measurement data from the infinite space between the stars and planetary systems for the first time. The Voyager mission is truly one of the boldest space exploration missions we humans have ever launched. The primary scientific objectives of the Voyager mission in the near future include the ongoing study of interstellar space. Voyager 1 and its sister ship Voyager 2 are the only man-made objects that have ever ventured into this unexplored realm. The further away the probes are from Earth, the more exciting but also the more difficult the mission becomes. It is already a miracle that we can maintain contact with technical devices that are so far away. The second critical point is the energy supply. The plutonium-based radioisotope generators on board the probes produce less and less energy over time. The mission teams have already switched off most of the instruments in order to reserve the remaining energy for the most important scientific missions. NASA is currently hoping that both Voyager probes will continue to transmit data until the end of the decade and possibly beyond. But even when the radio link has long since been lost, the mission will not end. The Voyager twins will then become ambassadors for our civilization and culture. Each probe is equipped with an extremely long-lasting golden record on board, which contains sounds, images, and messages from Earth. In many thousands of years, the probes may be captured by the gravitational pull of a star and then appear on the radar screens of another civilization. Voyager. Fast, cheap, reliable. It's hard to believe, but these two veterans of space exploration were put together in a few months on a mini budget to take advantage of a special window in the constellation of the outer planets. Saturn, Jupiter, Uranus, and Neptune had not been so favorably aligned for 170 years, and it was known in the 70s that it would take another 170 years for the four outer planets to come together again. So they took action and built the two Voyager probes in a rush. Both were to take slightly different courses, and if one was lost, the other would still have been there. In the end, both reached their destination. 1977 was the beginning of an epic journey. To increase their speed, both probes flew several maneuvers around planets. Voyager 2, launched on August 20th, 1977, reached Jupiter on July 9th, 1979. Voyager 1, which followed on September 5th of the same year, reached Jupiter in March 1979 and provided the first breathtaking images and valuable data about the giant planet and its moons. One of the most remarkable results was the discovery of volcanic activity on the moon Io. At the time, this was the first observation of volcanism outside the Earth. After the successful flyby of Jupiter, Voyager 1 continued its journey and reached Saturn in November 1980, revealing the complex structure and beauty of Saturn's rings and providing fascinating insights into the planet's atmosphere and moons, as well as the first detailed look at Titan, Saturn's largest moon. Voyager 2 investigated the aspects around Jupiter that Voyager 1 had missed. Together, the two provided a perfect picture of the gas giant and so many images that scientists still rave about today. Voyager 2 visited Saturn and continued its unique journey to Uranus and Neptune. During its flyby of Uranus in January 1986, Voyager 2 discovered 10 new moons and 2 new rings around the ice giant. The journey culminated in August 1989, when Voyager 2 became the first probe to fly past Neptune and send us the very first image of the planet. Voyager 2 discovered Neptune's Great Dark Spot, many clues to the most violent storms in the solar system, and previously unknown moons. After providing invaluable insights into the outer planets, the Voyager probes continued their journey beyond the confines of the known solar system. Their mission was extended to an interstellar mission, and NASA was amazed at the tenacity and reliability these 2 simple probes had shown up to that point. No one had initially hoped that the 2 would eventually reach the boundaries of the solar system, but they did, and researchers are very grateful for these moving moments. The first time in the heliosphere. It was a cause for celebration. Voyager 1 reached the heliosphere in August 2012. The enormous bubble in interstellar space created by the solar wind, the stream of charged particles emitted by the sun, envelops our solar system and protects it from cosmic radiation. The boundary of the heliosphere, where the solar wind meets the interstellar medium and loses velocity, is called the heliopause. Beyond this boundary, the influence of interstellar space begins. Compared to the incredible vastness of the universe, the heliosphere is only a tiny dot. However, it extends far beyond the outermost planets of our solar system. Voyager 1 was the first probe to cross the heliopause and entered interstellar space in 2012, about 121 astronomical units away from the Sun, the equivalent of around 18 billion kilometers. Although this is an enormous distance from our point of view, it's small compared to the size of our galaxy. The Milky Way has a diameter of around 100,000 light-years, which corresponds to 6,324,107,700 astronomical units. And our Milky Way is only an average-sized galaxy in a universe that is home to billions of galaxies. So the threshold of the heliosphere is really only a pebble's throw in cosmic terms. But for our science, it was a huge breakthrough that revealed some surprises. Expected results were the decreases in the solar wind and the increase in cosmic rays from outside our solar system. Unexpected, however, was the discovery that the magnetic field outside the heliosphere was stronger and oriented differently than predicted. Voyager 1 encountered a magnetic field that is more than 10 times stronger than the magnetic field inside the heliosphere. This discovery confronts us with completely new questions about the structure of the interstellar space and the interaction between the solar wind and the interstellar medium. Another unexpected result was the discovery of a magnetic highway at the boundary of the heliosphere. In this region, charged particles flow back and forth between the heliosphere and interstellar space, indicating a more complex structure of the heliosphere than previously thought. A surprising stream of particles that appeared after crossing the threshold to interstellar space added further mystery. Some scientists went so far as to suggest that we may have encountered the first traces of a new force of nature, or possibly discovered an alien signature. With each mysterious discovery that experts make in the Milky Way, we become more aware that we are still far from having unraveled all the secrets of our home galaxy. In the past, scientists came across some fascinating and puzzling objects in the center of the Milky Way, things that are still making renowned researchers scratch their heads. Strange glow at the Milky Way's center. The Milky Way is known to host thousands and thousands of sparkling celestial objects. Faced with the approximately 400 billion stars estimated to reside in our home galaxy, we quickly fall into the awestruck wonder. However, not every luminous structure in the Milky Way can be immediately placed in a known scientific context. The experts are also aware of this fact, which is why they are vigorously trying to decipher the mysterious glow at the center of our local barred spiral galaxy. Experts agree that there is a supermassive black hole in the galactic center of the Milky Way, which experts have named Sagittarius A star. However, in that central region, scientists also located a high-energy gamma-ray glow, which experts refer to as the GeV excess of the galactic center. For many years, astronomers have been trying to fathom the background of this enthralling phenomenon. One of the most exciting and hotly debated explanations is that the mysterious gamma-ray glow could be produced as a result of the annihilation of dark matter. However, research published a few months ago by a team of astrophysicists may now put an end to this controversial theory. Within their work, the scientists created a simulation model which dealt with the gamma-ray bursts in the center of the Milky Way. The experts came to the conclusion that the annihilation of dark matter as the cause of the ominous glow can be practically ruled out. Probably the largest problem that arises with investigations of this kind is the fact that the existence of dark matter has yet to be proven at all beyond a doubt within the ranks of scientists. It's rather a postulated form of matter with the help of which movements of visible matter can be explained. However, the study results published by the University of California astrophysics team now shake this theory to its core. The gamma-ray glow. The GeV excess of the galactic center was first detected when the Fermi Gamma-Ray Space Telescope began taking a closer look at the corresponding central region of the Milky Way more than a decade ago. It was during these scientific surveys that researchers finally noticed the mysterious gamma-ray glow. Gamma rays are the most energetic electromagnetic waves in the entire universe. The rays are generated mainly by impressive celestial bodies. These include so-called millisecond pulsars. These rapidly rotating neutron stars owe their name to the fact that their rotation time is less than 20 milliseconds. But also colliding neutron stars, supernovae, and black holes have been identified as sources of gamma rays in the past. However, when experts evaluated the data provided by NASA's Fermi telescope, they were unable to pinpoint the source of these high-energy lights. If we look at the statements of the Italian nuclear physicist Mattia Di Mauro, we realize how much scientists disagree about this controversial question. According to the analysis of the Italian, the source of the GeV excess is, contrary to the Californian research results, due to interactions with dark matter. As already mentioned, however, it is not possible for us at present to prove the existence of this postulated form of matter directly. All that suggests its existence are gravitational effects, which cannot be explained by the influence of visible matter. For example, galaxies rotate significantly faster than they should be able to, from a purely factual material point of view. Therefore, scientists are firmly convinced that the vastness of the universe is permeated by an undefined form of matter that causes the otherwise inexplicable gravitational effects. Although we cannot see dark matter or detect it by any other means, it is believed to make up about 80% of the total matter in the universe. The scientists Lisa Goodenow and Dan Hooper put forward the thesis that certain weakly interacting dark matter particles could collide with their antiparticles, effectively annihilating each other. This process should lead, among other things, to the fact that gamma rays are sent into the widths of the universe. Alternative explanations. As is the case with any unsolved scientific question, this is not the only thesis experts have advanced to try to explain the gamma-ray glow in the center of the Milky Way. About 3 years ago, another team of researchers concluded that it's primarily the influence of undiscovered pulsars that causes the galactic phenomena in our home galaxy. The fact that we have not yet seen the corresponding old dead stars is simply due to the fact that they have so far successfully eluded our terrestrial gaze in the crowded, dusty center of the Milky Way. However, recent investigations have revealed that the distribution of the GeV excess in the central region of the Milky Way is not uniform. This is strange, for if the annihilation of dark matter particles is indeed responsible for the gamma-ray glow, a uniform expression would be very likely. In fact, however, the gamma-ray emissions present themselves in a simplified speckled form. Many experts attribute this to the fact that the GeV excess would have solid point sources, like pulsars. It didn't take long, however, before this scientific thesis was also challenged. Disagreement among experts. Another team of scientists came on the scene, defending the thesis that the gamma-ray glow, despite its speckled distribution, could be produced by dark matter. However, the subsequent theoretical models created by other experts, which looked at the galactic center along with the hypothetical dark matter annihilation, painted a different picture. According to them, it is unlikely that the collision of dark matter particles and their consequent annihilation are the cause of the GeV excess. Does it mean in the reverse conclusion that this controversially discussed thesis was finally banished from the ranks of scientists? In fact, that's not the case. The Italian nuclear physicist Mattia Di Mauro refers above all to the extensive data set of the Fermi telescope, which the researcher uses within his studies. The scientist looks at its information that was collected over a representative period of more than 10 years. Specifically, the Italian compares the information collected by the Fermi telescope with the astronomical anomalies recorded by the Pamela detector. This was a technical module that had the task of studying cosmic rays. The complex device, which was attached to a satellite orbiting the Earth, was in service between 2006 and 2016. Di Mauro also includes the results of measurements taken by the alpha magnetic spectrometer on board the space shuttle and the ISS. If the excess of gamma rays were due to the interaction between cosmic rays and atoms, the spatial distribution of gamma rays would be directly related to the prevailing energies, Di Mauro said. Accordingly, there would be a larger spatial distribution at lower energies, while the spread should be much smaller at higher energies. However, the study by the Italian nuclear physicist shows that the spatial distribution of gamma ray excess is not related to energy. Moreover, such a circumstance has never been observed before in the universe, which makes the thesis that it's triggered by the interactions of dark matter more than ever the focus of scientific interest. In fact, most researchers currently assume that all dark matter particles have similar energies among themselves. The finding that the excess of gamma rays is unusually concentrated in the center of the Milky Way fuels the hypothesis that dark matter actually contains a completely new type of particle. The enigma endures. What this particle form is like, however, is still literally written in the stars. To approach this highly intriguing question, Di Mauro, in collaboration with his Swedish colleague Wolfgang Winkler, searched for gamma-ray excesses in nearby spherical dwarf galaxies. However, the galactic search of the two renowned researchers was not met with success. If one follows the statements of Di Mauro, this circumstance does not mean at all that their thesis is incorrect. According to them, the research results would help rather to further limit the potential mass of dark matter particles. As you notice, the current state of knowledge about the true origins of the gamma-ray glow still seems extremely diffuse. We can neither prove that dark matter influences are responsible for this fascinating phenomenon, nor that they are not. It will probably take several more years and much more research to get to the bottom of this cosmic mystery once and for all. Until then, we wait spellbound for new realizations scientists will come upon concerning this topic in the future. A strange void at the beginning of time may now confirm a remarkable prediction by Albert Einstein. Imagine how, 100 years ago, scientists slowly began to look beyond the edges of the Milky Way. What they saw astonished them. At first, it was just hazy nebulae. Then it became clear that these nebulae were other galaxies. First, the small and large Magellanic clouds became visible. Then, the Andromeda Galaxy, and finally, the shocked scientists realized how many more galaxies there were. Based on these findings, ideas such as the evolution of galaxies and the infinity of the universe were born. Then, Edwin Hubble observed that distant galaxies were moving away from us, and the idea of expansion was born. Shortly afterwards, the Belgian Georges Lemaitre came up with the Big Bang. This all took place slightly after the time when Albert Einstein presented his theories of relativity. Many of the researchers' purely theoretical predictions, which were made in the 1910s and 20s, were confirmed by the new discoveries. However, Einstein was unsure throughout his life whether the universe really had a beginning and an end, although he fundamentally accepted the Big Bang theory. Nevertheless, Einstein was always sure about another interesting question. Even if the universe did have a beginning and an end, he was certain that we would never be able to see this beginning and end, no matter how good our telescopes are. How did Einstein come up with this crazy idea, and what does it have to do with the void discovered by the James Webb Telescope? Albert Einstein's devastating prediction. Einstein was certainly one of the most important physicists of the 20th century, and he made many predictions that are still cornerstones of modern science today. One profound consideration was the aforementioned prediction that we could never directly observe the absolute beginning of the universe. And Einstein gave two interesting reasons for this. Firstly, the theory of the Big Bang and other theories based on it postulated that there was no light for hundreds of thousands of years immediately after the Big Bang. Today, scientists call this epoch the Dark Ages. So, how could we see a point in time or an event with telescopes when there was no light? There are even some exciting answers to this question today, such as radio telescopes. These do not see, but hear. But researchers are pretty sure that the Big Bang was not a loud expansion, but took place in complete silence. Basically, the space in which an audible explosion could have taken place did not even exist at the time of the Big Bang. Space itself only came into being with the Big Bang and was formed as a consequence of this event. Radio telescopes detect waves that are usually far from the audible sound spectrum. Space hardly conducts any sound. Only a few other waves penetrate the interstellar medium, which can be made audible using modern technologies. We would therefore not really be able to hear the presumably silent beginning of the universe. We discovered the cosmic background radiation back in the 1960s and have since mapped it very well. This radiation is considered to be an after effect of the Big Bang, and much evidence for the Big Bang has been derived from it. However, the microwave background has never led us directly to the Big Bang. So here too, we apparently have no way of detecting or proving the absolute beginning or Big Bang. However, Einstein was also of the opinion, for another reason, that we can never see all the way to the beginning or edge of the universe. He was of the opinion that the beginning would move further and further away from us due to the expansion and extension of the universe and would therefore be out of our range of vision, so to speak. Albert Einstein also believed at times in a curvature of all space. This means that the starting point could also be behind a kind of horizon that will forever obscure our view. Now, imagine again that this was at a time when the best telescopes were only capable of blurring neighboring galaxies. Today, we know of the existence of millions of galaxies. In a universe teeming with galaxies, expanding so much and getting bigger and bigger, it could be really hard to see far at all. But that's not true. Although our cosmos is so rich, the spaces between the galaxies and galaxy clusters are so large that we can now see 13.6 billion years away with our telescopes. That would be very close to the Big Bang, and with the James Webb Space Telescope, we are already pretty damn close. But the Webb telescope does not show us what scientists called the Big Bang 100 years ago. The JWST discovered a strange void. I'm sure you've heard that the JWST has discovered an extremely large number of very old galaxies that now even call the Big Bang into question. But did you also know that the JWST has discovered a strange void that could confirm Albert Einstein's prediction of the non-observability of the absolute beginning? Absolute voids are mysterious spaces in the universe that are so empty that they actually contradict the theory of relativity. But how can it be that they confirm Einstein's ideas about the invisibility of the beginning? This is initially explained by the fact that the emptiness was thought to be an indication of the Dark Ages, in which there was not much at first, at least no stars and no galaxies. Some researchers believe that the discovery had at least confirmed the existence of this epoch, but then came the shock. The darkness turned out to be an extremely distant void. We also know of closer and more recent voids. Here, these voids already pose puzzles, but in the extremely early universe, voids are once again scientific impossibilities. They do not fit into the idea of the homogeneity of the universe, which is directly linked to the idea of the Big Bang or expansion. Voids are too big and too strange. They have an inhomogeneous character and contradict some of the foundations of our cosmology. A void does not really confirm Albert Einstein's prediction. However, the Webb telescope seems to confirm the view of the brilliant scientist in another way. The telescope has so far found no trace of a beginning or an early stage of the universe. The images of the allegedly extremely early universe only show structures and galaxies that do not appear much different from those we know from the universe we can observe more closely. Could a void have been the beginning of the universe? The question now arises as to whether a mysterious void could have been the origin of the universe. We cannot completely rule this out because ultimately we never know what voids really are. And these days, we also have to admit that we do not know how the universe really began. Voids are probably empty, but we don't know that for sure either. It's possible that they contain some kind of matter that we don't know about yet. Imagine dark galaxies. Voids really are sometimes interpreted as some sort of parallel worlds, and some scientists see them as scar tissue from the collision of universes in the multiverse. Other crazy theories claim that aliens darken the galaxies in a void to harvest energy. So, you can already see that these mysterious voids challenge our scientists and lead to the craziest theories. Of course, it could be that our universe was created in a large void. The mere fact that we cannot prove the opposite reinforces such an idea. That leaves the question of how matter was created. What are singularities really? We have already talked about the nothingness from which the universe is said to have emerged. If that was the absolute starting point, how could we observe it? After all, it was nothing and therefore not detectable for us. A singularity is a point at which all forces are either so condensed that our dimensions of values and sizes fail, or everything that exists is concentrated into this one point. The point consisted of a fluctuation of possibilities that existed in a state of complete equilibrium. A previously unknown event is said to have disturbed this standstill at one point, and creation began. From this tiny point, everything that we know and can see today came into being. This means no less than that the information for you and me, all life on this Earth, every star and every exoplanet, was contained in this tiny dot of nothing. The question of how an infinitesimally small dot of nothing can contain everything is one of the great mysteries of science, and it's currently unclear whether we will ever be able to solve this puzzle. We find these mysterious singularities in another place in the universe, namely in the center of black holes. These in turn are found at the center of pretty much every known galaxy, and black holes are what remains when stars of a certain size explode. At least that's what scientists assume. No one has ever been in the center of a black hole, and, as we have now discussed, we have hardly any way of seeing the absolute starting point of the universe, if it existed at all. Everything is based on calculations that made sense until the James Webb Telescope discovered something different from what our theories postulated. The Webb Telescope shows that the universe must be much older than we assumed, or that its nature is quite different from what all our calculations predicted. An interstellar visitor. It is October 19th, 2017, when an absolute milestone is added to the list of astronomical discoveries. With the help of the Pan-STARRS telescope in Hawaii, researchers managed for the first time in history to identify an object within our native solar system that was classified as interstellar. As the name suggests, interstellar objects are astronomical entities that originate in interstellar space and are not gravitationally bound to a central star. However, this term is also used for those objects which are on an interstellar trajectory but temporarily pass into the immediate vicinity of a star. This was also the case with the exciting body discovered in Hawaii, which was to receive the official designation Oumuamua. However, by the time the object was added to the star charts, it had already passed our sun and was already on its way back into interstellar space. The first investigation of the orbital properties initially suggested that Oumuamua would be an ordinary comet. However, this assumption was soon overshadowed by big question marks, because actually, with a closer look, the structure possessed no comet-typical tail. But this would not remain the only riddle to follow this exciting discovery. The trajectory on the test bench. First, the experts had to take a closer look at the trajectory of this exciting object and reconstruct its possible origin. What was certain was that Oumuamua plunged into the solar system almost perpendicular to the orbital planes of the planets. Then, in early September 2017, the body had passed the ecliptic plane, the apparent orbit that the sun traces in the sky. Using this information, experts were able to calculate that Oumuamua had bumped towards us from the direction of the constellation Lyra, not far from the main star Vega. The object finally reached its observed maximum velocity on September 9, when it passed through the apex of its orbit at a speed of more than 45 miles per second, approaching within 23 million miles of the sun. A little over a month later, Oumuamua made close contact with our blue home planet. The closest distance between the object and us was about 14 million miles, which is about 60 times the distance between the Moon and Earth. But then it was time for the exciting object to take its leave. With gradually decreasing speed, Oumuamua took course in the direction of the constellation Pegasus, so that it is currently moving further and further away from our home solar system. But already, the analysis of the trajectory caused raised eyebrows among the ranks of experts. The deceleration the structure ran through on its flight in the direction of the sun was somewhat smaller than it would have been under the influence of gravity alone. One theory tried to explain the additional acceleration with the outgassing of volatile materials. However, this process would most likely have set in motion an enormous effect on the body's rotation, but no such change could be detected. A mysterious object. In order to determine what Oumuamua was actually about, the ominous structure was viewed by several modern telescopes. The unusually intense brightness fluctuations that were registered in the course of this suggested that the object had a cigar-like shape. However, the extreme brightness changes could not be explained by the rotation period of the body. Consequently, it seemed that Oumuamua is not rotating around one of its axes, but literally tumbling through space. The fact that no dust particles were found in the immediate vicinity of the body led the scientists to the conclusion that the mysterious body does not contain water and is probably composed mainly of rock or metal. Assuming that Oumuamua has become exceedingly dark as a result of unchecked bombardment with cosmic rays over millions of years, scientists suspect a very low albedo. Specifically, the albedo is estimated at a value of 0.04. However, this is only a theoretical number that has not been directly proven. If the assumed albedo is correct, Oumuamua would have an average diameter of about 600 feet. What the experts do know, however, is that the surface of the structure has a reddish tinge, which is attributed to the existence of organic matter. After Oumuamua was categorized as an asteroid a few days after its discovery, it's now again considered more likely that it's a comet after all. But these are still by far not all the theses proposed in the field. So some researchers pursued the approach that the body could be composed of frozen hydrogen, an exciting theory which turned out improbable due to further investigations. The possibility that Oumuamua could represent in truth a stick material ice fragment of a distant planet is discussed likewise in the ranks of experts. Equally, the most exciting as well as most controversial explanation approach departs from the idea that the mysterious structure is not at all a natural body, but the work of an advanced extraterrestrial species. An extraterrestrial spaceship? The unusual cigar-shaped form of Oumuamua alone fed the first speculations that it could actually be an extraterrestrial spaceship. This theory was then further fueled by the thoughts theoretical physicist Avi Loeb and Shmuel Bialy brought into the field. The two researchers came in the course of their work to the conclusion that the registered orbit deviation, which could not be explained by gravity, as well as the missing dust development, agree very well with the assumed characteristics of a very thin structure, pushed by the radiation pressure of our host star from its course. Consequently, it would be conceivable that the corresponding structure in truth embodies a complex solar sail, which was sent on its way into space by an extraterrestrial civilization. The rest of the expert world also became aware of this exciting thesis that Oumuamua was artificially created. To get to the bottom of this exciting hypothesis, the radio telescope at the Green Bank Observatory in West Virginia was pointed directly at the interstellar visitor. Through this endeavor, scientists hoped to possibly obtain signals that would indeed suggest an artificial origin for the object. Although it was considered exceedingly unlikely in advance that artificially generated signals from an extraterrestrial species would be found, the researchers saw their work as a worthwhile and unique opportunity. So Oumuamua was studied in detail over a period of 14 days. The evaluation of the collected data finally delivered the sobering realization that no signals were found that would point to an artificial background. In order to uncover the identity of this cosmic mystery, the experts are currently playing with the idea of simply turning the galactic tables. Now that Oumuamua has moved close to our blue home planet, it is now time for us to pay the entity a visit. On the trail of a secret. However, it's anything but easy for spacecraft of our time to intercept Oumuamua. For example, the hyperbolic excess velocity of the object is given at about 16 miles per second. By comparison, Voyager 1, the spacecraft with the highest current hyperbolic excess velocity, reaches only 10 miles per second. However, a sophisticated maneuver could still make it possible for us to reach this structure one day. The ignition of a solid fuel engine would literally shoot the probe out of the solar system. In this way, it would be possible to reach Oumuamua about 16 years after the launch of the spacecraft. However, the experts' ideas are still far from being put into practice. So when and if we will get to the bottom of the Oumuamua mystery is still literally written in the stars. Now we want your opinion. What do you think about the exciting interstellar visitor that is accompanied by so many questions? Write us your comments, your suggestions, and your feedback to today's video in the comments. In the mood for more exciting videos about the most mysterious objects in space? Then take a look at the other contributions on our channel, which you can access by clicking on one of the images in the credits. Thanks for your interest, take care, and we'll see you next time.